Hi, and welcome to Concept Based. I'm John Hepworth, and this is a Year 11 advanced topic that is the beginning of a whole exploration into another branch of mathematics. It's calculus. So, this is actually the beginning of the introduction to differentiation, which you have never done before in any of your Stage 5 syllabus at all, even in Path. This is new. So today we're not going to actually do the first step of calculus, but what we're going to do is we're going to talk about the concepts that lead to us wanting to do calculus with things that are practical applications. So this is a practical application here where we've got a distance time graph and we want to calculate the instantaneous speed at time equals 4. So with this graph, we've got time down the bottom here, and we've got distance up the side here. And what we're being asked to find is the instantaneous speed at time equals 4. Now, what you've done previously in stage 5 is you've approximated what the speed would be at a certain point by taking a range approximation. So for example here, what we could do to know what the instant speed that we're going at t equals 4 is we could look at an average of what speed we were going between 3 and 5. So if we went to 3 and we went to 5 and we drew a line between those two, help me out OneNote, didn't want to help me, let's try again. A line between those two, then we could go ahead and do that as an average. So for speed equals distance over time. So the distance that we're covering is the vertical part of this triangle, and the time that it's covering is the horizontal part. So what you might realize there is we're really talking about rise over run, which is really what we talk about when we talk about gradients. So what I suppose this question is leaning towards is it's asking us what is the gradient of this line right at this point. And that's what we use calculus for. So let's go ahead and make an approximation. So at my 3 value here, my graph, I'm just going to delete some things because I've drawn a lot, is let's say 3.1, and it goes down to, let's say, 2.3. So from 3.1 down to 2.3, we're going down 0.8. So that is going to mean my distance, negative 0.8. And we're running 2 seconds here. So we're going to divide it by 2. And so we're going to say that it's equal to negative 0.4. So our instantaneous speed would be negative 4 meters per second, approximately. Now, if we were going to do an instantaneous, well, let's have a look at what the line looks like that we've calculated. Help me OneNote. I'd love it if it helped me 100% of the time. There we go. And we're going to zoom in here, as long as OneNote allows me to zoom in. Sometimes it's not happy with that. Here we go. All right, so when we zoom in here, what we can see is that the line that we've approximated is really close to the instantaneous line there at t equals 4. And if I was to draw a tangent across there, you can see that these two lines here, the approximation I've made and the actual tangent, are almost identical because I've used a pretty good approximation. So what we can see then is that the instantaneous speed could actually be found by drawing a tangent to the line and then doing a gradient of the tangent. Now I've actually made a Desmos version of this this graph that we're seeing, and I've created little sliders so we can look at what it would look like by having a couple of points on the graph and getting some sort of instantaneous, there's my other point, so instantaneous speed. So we can see that as we go out and put our points further and further apart, we're not really drawing a tangent to anything. But the closer that those 2 points get to each other, the more and more it becomes a tangent. Now, I can't make these 2 points both before, because if I do make them both before, you can see that the tangent line disappears. And that's because when we're talking about rise over run, the run from one point to another point is 0, and you can't divide by 0. So the closest I can get on the one that I've created here is like from 3.9 to 4. And then I've done a little speed calculation here, and I've said, hey, can you just do the subtraction of the y values, subtraction of the x values, divide them by each other, distance over time. And it told me that it's negative 3.6. So my super rough OneNote sketch drawing got me a total, let's zoom out here, of negative 0.4. And my super accurate Desmos calculation, as close to the tangent as possible without going together and doing calculus, was negative 0.36. So pretty close. So the idea, this very first introduction to calculus, is the idea that sometimes we don't want to make approximations. We want to find things that are instantaneous. To find things that are instantaneous, sometimes we need to find a tangent to a curve. And to find a tangent to a curve, we need to know the gradient of that curve at a particular point. And that's what opens up calculus. That's what we're actually using calculus to try and find, is the gradient of curves at particular points. But we're not starting that today. That's going to start probably in the next video or the one after. But hopefully this idea of tangents gives you an idea that that's what the gradient of that line is at that point. If we move the points as close to possible to the point where they're touching, we get that exact tangent and we get that instantaneous speed in this in this instance.